The absolute value property of area. Welcome back, everyone. Before we dive into today's new concept, let's quickly recap what we've already covered. In our previous lesson, we introduced a very powerful tool, the determinant formula, which allows us to calculate the area of a triangle if we know its three vertices, specifically x sub 1, y sub 1, x sub 2, y and y sub 2, and x sub 3, y sub 3. As you remember, the formula is written as area equals 1/2 of the determinant of a 3x3 matrix, where the first column contains our x-coordinates, the second column contains our y-coordinates, and the third column is filled with ones. Now, while this formula is mathematically sound, there is a critical geometric and mathematical nuance that we need to address today. As we move forward, we have to look closely at the sign of the result, specifically, what happens when that determinant comes out as a negative number? Understanding the nature of area. Now that we've looked at the determinant formula for the area of a triangle in the previous slide, I want us to pause and think about the concept of area itself. In physical geometry, when we talk about area, we are referring to the actual extent or the amount of space covered by a two-dimensional surface. Think about it this way. Whether you are measuring the floor of a classroom or the surface of a small piece of paper, you are measuring a magnitude. In mathematics, a magnitude represents a size or a quantity, and by definition, a magnitude cannot be negative. You can certainly have an area of 0, which happens if our 3 points all lie on a single straight line, meaning they are collinear, but it is physically impossible to have a negative amount of space. This brings us to a very important realization, which we will explore in the next slide. If area can never be negative, why does our determinant formula sometimes give us a negative result? Let's find out. Why the determinant can be negative. Now, you might be wondering, if area is always a positive magnitude, as we just discussed, why does our determinant formula sometimes give us a negative number? Well, here is the key. While the area itself must be positive, the value of a determinant is more flexible. It can be positive, negative, or even 0. The reason for this sign change lies in something called the orientation of the vertices. Think of it as the direction in which you are walking around the perimeter of the triangle. First, let's look at counterclockwise orientation. If you list your vertices, that is x sub 1, y sub 1, x sub 2, y sub 2, and x sub 3, y sub 3, in a counterclockwise order around the triangle, the determinant will result in a positive value. On the other hand, if you list those same vertices in a clockwise order, the determinant will result in a negative value. This is a crucial point to remember. Since we have the freedom to list the vertices of a triangle in any order we choose, the determinant formula might yield a negative value depending entirely on the sequence of the points we pick. This brings us to our next slide, where we will see how we use a specific mathematical tool to fix this and ensure our area calculation is always correct. The role of the absolute value. Now, we have a bit of a mathematical conflict on our hands. As we discussed in the previous slides, a determinant can result in a negative number depending on the order of the vertices, but as we established earlier, physical area can never be negative. To reconcile this conflict, to bridge the gap between the signed result of the determinant and the positive nature of area, we apply the absolute value to the result of our determinant calculation. If you need a quick refresher, remember that the absolute value of a number is simply its distance from 0 on a number line, which means we ignore the sign and focus only on the magnitude. So let's look at our corrected formula for the area of a triangle. It is written as area equals 1/2 of the absolute value of the determinant of a 3x3 matrix containing x sub 1, y sub 1, 1, x sub 2, y sub 2, 1, and x sub 3, y sub 3, 1. I want you to pay close attention to the notation here, as it can look a bit crowded. The outer vertical bars denote the absolute value operation, which is our final step to ensure positivity. Meanwhile, the inner vertical bars represent the determinant itself, We will see exactly how this works in practice in the next slide with a concrete numerical example. Illustrative example. Let's consider a triangle with 3 specific vertices: point A at 0, 0, point B at 4, 0, and point C at 0, 3. In step 1, we are going to calculate the determinant using the first sequence of vertices. Following the order from A to B to C, we set up our 3x3 determinant with the x-coordinates, y-coordinates, and a column of ones. Specifically, the first row is 0, 0, 1, the second row is 4, 0, 1, and the third row is 0, 3, 1. We'll refer to this determinant value as delta 1. To solve this, we will expand along the first row. We take the first element, 0, and multiply it by the determinant of the remaining 2x2 matrix, which is 0 minus 3. Next, we take the second element, 0, and subtract the product of 4, 0, and the remaining 2x2 matrix, which is 4 minus 0. Finally, we take the third element, 1, and multiply it by the determinant of the remaining matrix, which is 12 minus 0. When we perform these calculations, we find that delta 1 equals 12. To find our final area, we take 1/2 of the absolute value of 12, which gives us a final area of 6 square units. Now that we understand why the sign of the determinant can vary, let's put this theory into practice with an illustrative example. Notice that in this specific order, our determinant came out positive, but as we will see in the next slide, changing the order of these points will lead us to a different sign, even though the physical area remains exactly the same. Illustrative example continued. Now let's continue with our example to see this concept in action. In the previous slide, we calculated the area using the order A, then B, then C, which gave us a positive result. Now in step 2, let's see what happens if we reverse that order. Let's calculate the determinant using the sequence A, then C, then B, looking at our new matrix. The first row is 0, 0, 1, the second row is 0, 3, 1, and the third row is 4, 0, 1. When we expand this along the first row, we multiply 0 by the determinant of the 2x2 matrix, containing 3, 1, 0, and 3. Then we subtract 0 multiplied by the determinant of the matrix containing 0, 1, 4, and 1. And finally, we add 1 multiplied by the determinant of the matrix containing 0, 3, 4, and 0. Following through with the arithmetic, we get 0 times the quantity 3 minus 0, minus 0 times the quantity 0 minus 4, plus 1 times the quantity 0 minus 12. This simplifies to 0 minus 0 plus negative 12, leaving us with a determinant, delta 2, equal to negative 12. This brings us to step 3, where we apply the absolute value. As we discussed earlier, even though our determinant calculation resulted in negative 12, we must remember that area, as a physical magnitude, cannot be negative. So we apply the absolute value to negative 12, which turns it into positive 12. When we multiply this by 1/2, we get 6 square units. To conclude this example, notice that even though we changed the order of the vertices, which flipped the sign of our determinant, the absolute value ensured that our final answer remained a consistent, positive physical quantity of 6 square units. This perfectly illustrates why the absolute value property is so essential. Now, let's wrap up with some key takeaways to solidify what we've learned today. Key takeaways. First, let's remember the fundamental physical property. Area is always a non-negative quantity. As we discussed earlier, whether you are measuring a triangle on a graph or a piece of paper, you can never have a negative amount of space. Second, we have the determinant property. As we saw in our step-by-step examples, the sign of a determinant is sensitive to the order of your points. If you swap the rows, which is essentially just changing the order in which you list your vertices, the sign of the determinant will flip from positive to negative or vice versa. Third, this leads us to our necessary mathematical correction. To bridge the gap between a determinant that can be negative and an area that must be positive, you must always wrap your determinant calculation inside absolute value signs. This ensures that no matter which direction you trace your vertices, your final result is always positive. Finally, let's look at the complete, corrected formula one last time. Area equals 1/2, of the absolute value of the determinant. All right, let's bring everything we've discussed today together with a quick summary of our key takeaways. Now, before we wrap up, I want to point out a few common pitfalls to avoid in your future calculations, so let's move on to the next slide. Common mistakes. First, a very common error is simply forgetting to apply the absolute value. I have seen many students calculate the determinant, arrive at a negative number, and then either leave the area as a negative value or, even more concerning, just drop the negative sign without actually understanding the mathematical reason why they are doing so. Remember, as we discussed in our earlier slides, the negative sign is a result of the vertex orientation, but the area itself must be positive. To stay mathematically rigorous, always use the absolute value notation in your steps. Second, please be careful not to confuse your notation. When you are looking at the formula, you will see two different types of vertical bars. You have the inner vertical bars, which represent the determinant. That is, the specific process of calculating the value from the matrix. Then, you have the outer vertical bars, which represent the absolute value. It is vital to distinguish between the determinant as the calculation process and the absolute value as the final step used to ensure a positive magnitude. Finally, watch your application of the 1/2 constant. While you will find that the final numerical result remains the same whether you multiply by 1/2 before or after applying the absolute value, I want you to maintain consistent logic. Treat the determinant calculation and the absolute value as the core of the area calculation, and then apply the 1/2 to find the final area. Now, as we wrap up this lesson, I want to touch on some common pitfalls that students often encounter when working with this formula. Being aware of these mistakes will help you avoid losing marks in your exams. By keeping these points in mind, you will ensure your work is both accurate and mathematically sound. Great job today!